The YouTube channel name is ECE4760, and there's some video up there already. Students have been uploading video for about 3 or 4 years now, but they've been putting it random places with random names. And so I'm trying to get it all into one spot. Truth be known, I didn't know before last week you could make a channel, but you know, you learn slowly. Would you like to stand up and turn off that thing that's shining in my eyes up there? Press once, then press again. Thank you. And it's quieter too. So last time we started talking about the interrupt structure of this CPU. I want to finish talking about the interrupt structure of the CPU and then start writing some code. But first I guess I need to say that there's now 100 people. Only two people have dropped. And I guess I wasn't mean enough. But this is the current statistics. 22 on Wednesday, 31 Wednesday night, 17 Thursday, 30 Friday. That's acceptable. That'll work. As long as nobody changes into these two sections. You can change out of them, but not into them. So you can change into Thursday or Wednesday afternoon, but it's acceptable now. We'll survive. The room won't get too steaming. Any questions about the last lecture? I know there's lots of questions about the code because I've heard some of them. We'll talk about that for the rest of the lecture almost. Anything? All right, well let's I think I was just starting to talk about the hardware mechanism of the interrupt on this CPU. And when I realized I was out of time. So in your code, which we're going to talk about in a few minutes, you're going to have a main program, of course. You're going to write some functions that main calls, but you're also going to write some interrupt service routines that are not called directly by software, but rather respond to hardware events. So the interrupt structure is going to be such that some hardware event, there are no software exceptions on this processor. Some hardware event occurs. Having said that, see if somebody can figure out how to trigger an event from software. Think about it. Very good. Actually, you don't even need to do that. You don't have to send it from one pin to another. You can trigger an interrupt. You can set a pin to be an output, but trigger an interrupt when it goes high on an input. And if you put a high voltage out on the output, it takes the interrupt. Good. Okay, so we have a hardware event. Some hardware event, timer goes off, pin changes state, something of the sort. And this is going to set some flag in some register for one of the timers. It's TIFR0, timer interrupt flag register 0. You don't mess with those flags. You neither set them nor clear them. The hardware does that. But there is a register you can get to if for some reason you want to clobber an interrupt. You can do that. I suggest don't mess with it. So a flag is set in some register someplace. Then the CPU finishes the current instruction. Unless interrupts are turned off. For instance, by default, interrupts are turned off if you're in an interrupt. Now, you can override that with caution. But for now, you probably want to leave interrupts off in interrupt service routines, so it finishes the current instruction or the current ISR. Then the hardware pushes the PC. So this is an atomic operation. It is not interruptible, nor is it available from software. It is atomic. It happens as a unit. You push the PC, and on the same cycle, you clear the I bit, which turns off interrupts. The I bit is the master interrupt bit. It exists in SREG, which is memory or interrupt or IO location 3F, I think. Clears the I bit. Then CPU jumps to the vector table, and from the vector table, and clears the flag. That flag clears the flag that caused the interrupt. So that flag is cleared before you get to the interrupt code, before you get to the ISR, and then jump from the vector table to the interrupt service routine. At that point, control is returned to C code. The C compiler, this particular C compiler, automatically saves the state of the machine for you unless you turn it off. And so the compiler then saves the state. Then you have your code to deal with the event, whatever it may be. And then C restores the state and does a return from interrupt. So on the cosmic scale of things, it's fairly automatic. It does a lot of stuff for you. You can pretty much just write whatever variables you need to have modified. And as a general rule, for your own sanity, keep your interrupt service routines as short as you can. Because bugs in interrupt service routines are really hard to debug. For instance, you can't put a print statement in an interrupt service routine because it will clobber the interrupt handler. Because it takes so long to print something on a terminal. If you have a 1 millisecond time base and you try and debug it, you have not even time to print one character on the LCD before the next interrupt comes along. Because a flag is set, you essentially have a memory of 1 deep for a pending interrupt. So let's say that timer 1 goes off and sets a flag in TIFR 1, and a microsecond later a timer 0 goes off and sets a flag in TFIR 0. That 0 flag will be remembered until you get done with the timer 1 interrupt. But if you take 2 timer 0 interrupts, then 1 will be forgotten. So you have a memory of 1 event deep for each different interrupt source. Before I start talking about any questions on this? Okay, before I start talking about code, you need to know a little bit about how the STK500, we have a development board called an STK500. You've probably seen pictures of it on the Lab 1 site. So your MCU has some I/O pin on it, and the question is, how are these I/O pins physically wired to the LEDs and the push buttons? Because that'll determine whether a logic low or a logic high turns on an LED. Turns out that the original MCUs for which this system was designed had a bigger transistor pull-down resistor than pull-up resistor, and so it could sink more current than it could source. And so the LEDs were set up so that a low voltage on the pin turns them on. So the LEDs are inverted logic. A low on the output pin turns on the LED. And for an I/O pin, for an input pin, push buttons are set up so that when you push a push button on the board, you get a low input. Any questions about the homework? Speaking of high and low values and Thevenin equivalents and so on. All right, so let's write some C code here. I've already heard from a couple of people that my style differs from 3140 style. That's okay. You can code it any way that works. There are 3 demo codes. There's three almost templates for Lab 1. It's the only lab for which there are anything like a template code. The first one is basically how do you generate a 1 millisecond time tick and use it to schedule events. Very much like what you're going to need to do for Lab 1. The second demo code is more on timers. It's more about measuring external events, getting the period of a square wave coming into timer 1. Very much like you'll have to do for Lab 2. And there's also a little bit of code for how to program up the LCD, liquid crystal display. But in this particular example, main just schedules 3 functions, 3 tasks, so to speak, but they're really just written as functions. The timer 0 ISR decrements 3 counters. So the timer 0 interrupt service routine is going to effectively build 3 virtual timers, 3 1 millisecond timers. Task 1 is going to blink an LED. A blinking LED at either 2 or 8 hertz, depending on a button push. Task 2 is going to blink an LED at 1 hertz. And task 3 is going to look for a button push and signal task 1. So these are all very lightweight routines. Each one of them takes much less than a millisecond to execute. And so we can afford to have a really stupid scheduler because it's easy to meet the deadlines. Any questions? Okay. And so now we start to plow through the ugly code. And there's a bunch of stuff you have to include. You have to include, well, you don't have to include int types, but that's useful if you want to use CPU independent type names, like instead of car, you can use uint 8, which is an unsigned 8-bit integer, which is the same as a car. You also need to include AVR /IO.H. This has a big table in it that has the logical names of every I/O register and every pin name or register bit name, which is defined in the Mega 644 data sheet. So every name like TCCR0A and OCR or OC0IE enable, whatever, it's all there. So you can use the logical names and never have to go to the register number or bit number. You will almost always in this course include AVR interrupt.h, which has just 2 or 3 macros in it that allow you to easily set up interrupt service routines. Everything you write in this class will have an interrupt service routine in it. And then, of course, if you want to actually use character I/O, you have to include STDIO, standard I/O, which is takes care of put car and get car. It gives a method. It gives a function for your program to get to the serial interfaces. Although, as part of that, you also need to include UART.H. This is not part of the normal distribution. This is beerware from some guy. Beerware means if you like it, send him a beer. Strange concept. And UART.H has some more information about baud rates and how fast you want to send stuff across the serial link. Then we're going to, I usually do some defines, and one thing I like to define, which most C programmers really hate, is I like to define begin as curly bracket and define end as the other curly bracket. And the reason I like to do that, C programmers hate it for a number of reasons. One is that context-sensitive editors can't detect begin and end, and so they don't appropriately collapse and expand the code. And I like it because with my aging eyes, the difference between this bracket and this bracket is about 2 pixels. And if you're working on your laptop in some 6-point font, I can't debug it. So I can barely debug it on my own screen with a 11-point font. So either, if you want me to debug your code, either use begin and end or jack up the font size when I have to look at the code. I didn't actually hear any groans of disgust, at least with that, which was last year. I'm also going to define 3 times which are going to be used by the scheduler to time the 3 different tasks. So T1 is going to be set to a value of 250. These are going to be copied into byte length variables, byte length memory locations, and so the maximum size they can possibly have is 255, unsigned. T2 is going to be 125, and these will translate into milliseconds. And define T3 as 60 milliseconds. When you're writing Lab 1, you're probably going to find that you're going to need some task, some process that executes about once a millisecond to detect when the human has actually pushed the button. But you're going to need another task that executes about once every 200 milliseconds to update the LCD, because the LCD is so extraordinarily slow that if you update it once a millisecond, it will show nothing. And so you need to have one process running quite fast to capture the button push, and another process running quite slowly to update the LCD. And so you're going to have to break down the problem at hand into different speed categories and probably arrange your code in that fashion. For which this is clearly related 2 hertz versus 1 hertz. Right? And then we're going to define some volatile. Is it atyl? I spell very, very badly. And I often invert letters. You know, P's and B's and D's and Q's are just all circles with lines in different directions. I want a volatile unsigned car time 1 time 2 time 3. These variables, these memory locations, are going to be shared. They're going to be set in the interrupt service routine, and they're going to be read in main. So why do we need the volatile key word?
You don't have volatile the compiler doesn't know to reload the value from memory.
That's right.
So just keep it in the register.
And so you could have an incompatible version in the register because the compiler doesn't know to reload it from memory, and the interrupt service routine has trashed memory while it has corrected memory, has updated memory, and main still thinks it has a register variable which is valid. It's even worse than that. In this particular compiler, the compiler is an optimizing compiler, and it'll say, this variable is never set in main. She doesn't need it, and eliminates it completely from the code. And the symptom will be nothing happens, because these are going to be used to time out tasks. The variables never get set because they don't exist, and so none of your tasks ever run. We also need unsigned. You don't want to make everything a variable, a volatile, because that doesn't allow the compilers to do as much optimization. So you have to be a little careful about making everything a volatile, although there's a tendency for students to do that because you don't have to think as much about what's shared. So we're going to do an unsigned car, which is going to be, well, task 2, it turns out, needs a counter because of the way I wrote the code. And the reason it needs a counter is that I need to count up to half a second, which is 500 milliseconds, but I only have a 1-byte variable, which is only good for 255 milliseconds, so I'm counting to 125 4 times. So I need a counter that counts from 0 to 3 here. Furthermore, we need a task 3 message, which is what's going to be, so to speak, is going to signal task 1 that task 3 has seen a button push. And I'm kind of dividing this up more than it probably needs to be, but after all, this is an example. I mean, in any real code, you'd probably just check for the button in task 1. There's going to be another unsigned car, which is called LED, which holds the state of the LEDs. And an unsigned int called time, which is going to hold a value of milliseconds since last reset. So this is going to be running CPU time, so to speak. Any questions? Now, there's no operating system running. There's no place for a stream-oriented I/O to go unless you define it. And there's a small library that allows you to define a variable of type file. And we're going to define this to be UART string. And it's going to be set to the value f dev set up stream. So this sort of simulates the Unix stream environment with the function UART putCar, which tells the system how to copy a variable from the code to the universal asynchronous receive transmit. UART getCar, which tells it how to receive a character from the USART, and then some obscure flag. Well, it's not obscure. Set up read write. That's for compatibility with something. I have no idea what. But the cool thing is that if you want to go in and recode your own functions here, you can cause all of the serial I/O functions like sprintf, printf, scanf go to any device which is stream oriented just by changing putCar and getCar, which together are a total of probably 20 lines of code. So you can output stuff anywhere. Okay, so having done all that definition stuff now, let's write the interrupt service routine. So we're going to write, there's a macro ISR which flags this function that we're going to write as an interrupt service routine. We name it timer 0 underscore comp a vector vect. So this identifies to the compiler that we are writing interrupt code for timer 0 compare a channel interrupt. As you remember, that's the channel which supports a reset on match and an interrupt on match. So this is the appropriate thing to use for timing out a precision time. And then my beloved begin. Instead of a bracket, you can use a bracket. You know, it's okay. And then we're just going to, in the spirit of keeping interrupt service routine short, all I'm going to do in the interrupt service routine is decrement 3 counters, which will become our virtual timers. Yes?
I still get a little bit confused. So does that mean I should write that as R parentheses that line stuff at the beginning of the code, or that's the syntax practices should be the name of that piece of function?
Say it again, please.
So does that like ISR parentheses the name like as a line of code?
It is a line of code.
Okay.
It is ISR is actually a macro which takes this parameter and does something with it.
Okay.
Yeah.
So is that VET or is that
VECT.
Okay.
VECT. And those those names are all in the io.h file also, way at the end, hundreds of lines down.
Does that macro give you a function header for that?
Yes, it gives you a function header.
Does it set the right date does it set the interrupt vector?
Yes, it sets up, it builds a function and it sets up the interrupt vector to point to this function.
All right.
So that's very nice.
Yeah.
So if time 1 is greater than 0, then we're going to decrement time 1. If time 2 is greater than 0, we're going to decrement time 2. If time 3 is greater than 0, we're going to decrement time 3, and then end. So all the interrupt service routine does is to quickly find out if the timer variables are 0 and decrement them otherwise. Now then main, now let's write main next. And what we're going to do here, it's slightly confusing that main returns an int to nowhere. But that's the way they wrote the compiler. It gives a small warning which you can ignore if you use a void here, but I like to try and write code that doesn't throw warnings. So int is the return type of main. We're going to begin. And then there's going to be some initialize, which will be a function that has a whole bunch of low-level stuff in it. It'll set up all the I/O ports and the timers and all that, and we'll write that out in a few minutes. And then, as you know, every embedded program has a function that never exits, has a loop that never exits. So, while forever, begin. If time 1 equals 0, then, oh, I used the curly brackets here because I wanted to be a little terse and put it all on one line. Time 1 equals t1, and then we're going to do, then we're going to call task 1. C has this annoying ability to treat this structure in here as a statement. So if you wrote this instead, if you mistakenly wrote this as time 1 equals 0, what happens? It evaluates what's inside the parentheses first. It sets time to 0, and then it says, is time equal to 0? And the answer, or actually, it doesn't say is time equal to 0. It says is time not 0, and it never enters. So if you want to be obsessive, don't write it this way, write it this way. If 0 equals time 2, that way, if you leave out one of the equals, it'll throw an error because you're not allowed to assign anything to the value 0. All right. There's a really good paper, a web page actually linked up on the page. I had a lot of fun reading. It's how to write C code that you can't understand. And this is one of the things that's suggested to avoid. So again, we're going to say time 2 equals T2 task 2 bracket. And clearly what this is going to do is sort of reschedule the task for this much time in the future. If 0 equals time 3, then time 3 equals T3 task 3. And then we end the while, and we end main. Questions? So the effect is going to be then that task 1 is going to execute every, what did I say? Every 250 milliseconds. That means it'll blink the LED at 2 hertz. Right. Half a cycle on, half a cycle off, half a cycle on. It's toggling it every 250 milliseconds. So because this task is scheduled every 250 milliseconds, LED 1 will blink at 2 hertz. Unless we fiddle with time 1 in task 1. Task 2 executes every 125 milliseconds. But what we'll find is that inside task 2 there's a counter that counts up and only toggles the LED every 500 milliseconds for a frequency of 1 hertz. Yes?
Why did you put that in the ISR again?
What in the ISR?
The whole contents of that while loop. Instead of having a loop.
This is not in the ISR.
Yeah, right.
It is not.
So, why is it more advantageous to have the CPU run an infinite loop the whole time, instead of putting the body of the loop inside the ISR, so every time the timer runs, you can check?
Okay, because sooner or later the code will become so long, or you'll have some process which is so slow that you cannot put it in the interrupt service routine. Also, I mean it quite seriously, to maintain your sanity, don't put a lot of code in the interrupt service routine. Set a flag, let some task deal with the flag. Unless you need microsecond accuracy. So if you're doing audio synthesis, for instance, which you will be doing in Lab 3, there, in that case, the entire sample synthesis code must be in the interrupt service routine so that it is completely synchronous at 8 kilohertz. All right. For this, you're timing a human. Let's say that you're off by 30 microseconds. Who cares, right? So you do have to worry about the content. You have to worry about error budgets here. You have to worry about how much slop time you have. If you don't have any time you can play with, you have to put the code in the interrupt service routine. Otherwise, you should not put it in there. Yes.
Why are time 1, time 2, and time 3 cars instead of ints or something?
Why are they cars instead of ints? Because I originally copied this code from the assembly language version I originally wrote, which was an 8-bit assembly language version. And I didn't modify the logic from the assembly language version. There's no reason. If you used ints for the time, then you wouldn't have to do counts within the loops. Where was I? Oh, yes. Anything else? Okay. I used to code stuff up with everything in the interrupt service routine. And you get to some level of complexity and you can no longer figure out what the hell's going to happen. Let's do initialize. So in initialize, we got to set up, we got to do all the low-level stuff. So in particular, we're going to make 4 bits of port B an output. So because we're going to hook the LEDs to port B, so we're going to set DDRB to 0x0f. That sets the low 4 bits to output and the high 4 bits to input. We're going to set port B to 0. That turns on all the LEDs. It turns on 4 of the LEDs that are hooked to the 4 bits here. We're going to set DDRD to, we're just going to turn on 1 bit. I'll write it 2 different ways. We can write this as 0x02. That turns on bit 1 as an output. The reason for turning on bit 1 as an output is that bit 1 of channel D is the UART transmit line. So that's what will be hooked to the terminal. We should probably instead write this as DDRD is equal to 1 shift shift port D1. Then we're going to set up timer 0. That's going to require 4 statements. So TIMSK0 needs to have the output compare interrupt enable timer 0 channel A set. So we're going to shift a 1 into position OCIE0A. We're going to set the compare register OCR0A to 249 decimal. Remember, it's a 0-base system. We want 250 counts to make 1 millisecond. We're going to set TCCR0A, the control register A, to turn on WGM01. This enables the clear on compare match function. So that enables clear on compare match. Then we're going to set TCCR0B to 3. 0 binary 00000011. Because That is the bit pattern for the prescaler divide by 64. So those 4 statements set up the timer. If you leave this one out, it'll never interrupt. If you leave this one out, it won't reset on match, and so you'll get the wrong time. Given that we wrote an interrupt service routine for the compare match, then this is the only bit you dare turn on in that register. Now there's some state variables we have to set. We're going to set the LED state variable to 0xFF, which is all LEDs off. We're going to set the time 1 to T1, time 2 to T2, time 3 to T3, the task, what was TSK2 count, we're going to set to 4. We're going to set TS3 message, task 3 message to 0, saying the button has not been pushed at reset time. And then we need to initialize the USART so that you can send information to the terminal. So there's a UART init, which mostly just sets up the baud rate in the hardware. And then a very Unix-like thing, we're going to set std out, standard out, equal to standard in equal to standard error equal a pointer to UART underscore string. And then just to make sure everything is happy, we're going to do an fprint f to standard out. In Unix, standard out is where all communication with the terminal goes except for errors. Errors go to standard error. All input from scanf comes from standard in. So these are kind of vestigial Unix devices that don't actually exist for this system because there's no Unix. But we have standard out here. Fprintf is going to go to standard out. And we're just going to say starting, and then do a \n\r, end quote. \n\r is the primitive serial code for start writing on a new line and start writing at the beginning of the line. If you put in the /n, you'll write something and then the next line will start here. If you put in a /r and no n, you'll write a line and the next line will be here, over the top of it. This is really crude. Back in the days when these were physical teletypes, these were physical printers. The last thing we absolutely have to do to init the system and get everything working is we have to use the C call, SEI, which sets the interrupt enable bit. It sets the master enable, interrupt enable bit and turns on the whole show. Until that is set, no interrupt will be taken. The timers will do nothing. the timer counter is actually running, but it won't do anything useful in your program. And then we have to end initialize. Any questions?
So, you set port B all low. You have 4 outputs.
Yeah, it turns out that if you set an input low, it doesn't do anything except turn off the pull-up resistor.
Okay, so, well, I mean, I guess my question is because over there when you say LED is equal to 0xFF, you're automatically turning all of them on.
I'm turning them all off, but only 4 are actually connected.
Okay, so the only purpose of port B is equal to 0 is to disable the pull-ups.
Yes, for the inputs. What will happen is as soon as you execute this piece of code, 4 of the LEDs will turn on. And that's a useful indication that the code's running. Now, it won't turn on for long because as soon as one of these things times out, they'll go off. But you can usually see them flash. And that's comforting. If you see the LEDs come on, but it never prints starting, that suggests that you have trouble in this UART code someplace. If you see the lights come on, it prints starting, and then nothing at all happens, you probably left this out. Because everything up to here is inline code, no interrupts running. After that, the whole system is going to be executing at the beck and call of the interrupt system. What else?
You can read like standard out in and
Standard out, standard in, standard error equals ampersand UART underscore string. All of the codes that I talk about in lecture are online. So you don't have to copy them down. You might want to read through them before the lecture. I'm going to be talking about the other 2 examples next time. See you next week.